Hey guys, Dr. Betts here, coming up with another fantastic chemistry video, and today we're going to talk about orbitals. Orbitals, S's and P's and D's and F's. We're going to stick with S's and P's though. And we're going to talk about hybridization today. Hybridization is a very important concept in organic chemistry and in all chemistry in general. Have you ever wondered, when you look at orbitals, you have an S, you have a P. We all know the p orbitals are at right angles to each other. The s orbital is a sphere. How do we get tetrahedral? P orbitals are right angles to each other. We know that bonding happens through orbitals. How do we get tetrahedral if p orbitals are 90 degrees from each other? Very interesting question, right? Never thought of that before, did you? Well, today we're going to talk about why that occurs. Now, oops, sorry about that, guys. I went through it too fast. Play. There we go. There we go. Now, we're going to do what's called hybridization. We're going to do hybridization of orbitals. It's a very important concept in chemistry, hybridization. Now, we're going to take the s orbitals and the p orbitals and we're going to hybridize them together. And we're going to make new, what are called hybridized orbitals, and those will help us learn about and understand bond formation. Okay? Now, there's this thing called conservation of orbitals, which basically means if you start with 4 orbitals and you mix them together, you're going to get 4 orbitals back out. If you start with 2 orbitals and you mix them together, you're going to get 2 orbitals back out. You're not going to get more orbitals. You're not going to get less. You're going to get a conservation of orbitals. 2 kinds of bonding. Now, so far in your chemistry life, you've talked about single bonds, double bonds, triple bonds. Now, we're going to get a lot more specific. We're going to start talking about sigma bonding and pi bonding. Sigma bonding, the electron density lies between the nuclei, just like all bonding. A bond may be formed by the combination of an s orbital to an s orbital of another atom, 2 p orbitals of 2 different atoms overlapping, an s or a p orbital overlapping, or hybridized orbitals overlapping. Okay? Basically, a sigma bond is the head-to-head overlapping of orbitals. That's how sigma bonding works. Pi bonding, on the other hand, are the sideways overlap of 2 parallel p orbitals leading to a pi bonding situation. Imagine sigma bonding is when orbitals overlap head-to-head. Pi bonding is when they overlap side by side. So the orbitals here and the orbital here are kind of blending slightly together on the top lobe and the bottom lobe of a p orbital. And that's called pi bonding. We're going to get into that a little bit more. I'm going to show you a lot more about pi bonding and sigma bonding as time goes on. Molecular shapes. The 3 basic molecular shapes in organic chemistry. There are more you have to know. Tetrahedral, trigonal planar, linear. You should already know what that means. You should already know how to figure that out. There's also pyramidal. There's also bent. And there's a few others I'm probably forgetting, but these are the top 3. Tetrahedral, trigonal planar, linear. There's also pyramidal and bent. Those are the big ones. Okay? So those are the shapes you have to know. If you don't know them, write them down. If you don't know how to figure it out, go back to your Gen Chem notes and figure that out. Oop. Sorry, I meant to talk about that. I'm having a bad day today, guys. Here we go. There we go. Now, like I told you, the bond angles of all of these things can't be explained by unhybridized orbitals, S and P's. P orbitals are 90 degrees from each other. This does not work. Now, in Vesper theory, you guys understand that this is how you predict molecular shape. You should know how to do that. The nice thing about hybridized orbitals is that when you mix them together, they have a lower energy because the electron pairs are further apart. Okay? They're going to be a lot further apart than 90 degrees. In a p orbital, you're 90 degrees apart. In a hybridized orbital, you are as much as 180 degrees apart, depending on how you're hybridized. So it's a better situation in a lower energy situation for the electrons. The first hybridization we're going to talk about is sp3. Stands for 1 times s, 3 times p, to get 4 times sp3 orbitals. Okay, remember the law of conservation of orbitals. We have 4 orbitals going in. We have 4 orbitals coming out. Now, notice these are p orbitals. This is an s orbital of the sphere. Notice how the sp3 orbitals are long, elongated, and rounded. They're elongated and rounded. And they fit together with a bond angle of 109.5, which is tetrahedral. That's the bond angle of a tetrahedral. So this is how tetrahedral things are hybridized. They have sp3 hybridization. Okay? And this explains a little bit about why carbon will adopt why carbon will adopt a tetrahedral if it has 4 single bonds. Okay? sp3 hybridized. Now, let's take a look at this. All right, guys, now that we've learned a little bit about sp3 hybridization, let's look at an example of it. Methane, CH4. I think everyone here probably knows what methane is. There we go. I'll make that a little bit prettier than that. There we go. Now this is sp3. I know that because there's no multiple bonds and there's 4 electron groups. So 4 electron groups, no multiple bonds, sp3. Here's how it's going to look. We have carbon. And from that carbon, we're going to have an sp3 orbital that looks kind of like this with a hydrogen. And we'll have another sp3 orbital that looks kind of like this. Now again, I'm not Rembrandt here, guys. I'm not trying to be an artist. I'm just trying to do this as best I can. Now this one here I'm going to draw really dark and heavy to give the illusion that it's coming towards us. Now I can do a little better than that. There we go. That's a little better. Remember that little nubby back there? I'm going to try to give the illusion that this orbital is coming towards me. Hydrogen. And then I'm going to draw this one dotted to give the illusion that the hydrogen is going away from me. Okay? Now, this bond angle here is 109.5. This is a sigma bond, which is abbreviated with the Greek letter sigma. That is also a sigma bond. That is a sigma bond, and so is that. With the Greek letter sigma. Now, all sp3 atoms have this hybridization structure. They all have it. Okay? And that's kind of how they're drawn. So let's look at sp2 hybridization. Now, sp3, we had 1 s orbital and 3 p orbitals hybridizing. Now we're going to have 1 s orbital and 2 p orbitals hybridizing. And notice we're going to get 3 hybrid orbitals. Now check it out. They look basically the same as an sp3. They're a little bit shorter and a little bit fatter than sp3 because they have more p character, less s character. So, but essentially when you draw them, they're going to look the same, especially if you draw them by hand. You're going to have a trigonal planar geometry, and the bond angle is going to be 109 degrees. I guess that's off camera, isn't it? There you go, 109 degrees. And there is a computer-generated version of it. Now here is an unhybridized p orbital. Okay? Notice the bond angle between here and here is 120. So the bond angle between sp2 orbitals is 120, but the bond angle between the p orbital and the hybridized orbital is 90. Okay? So that's important to know. The p orbital is still there. It just didn't get hybridized. It's still there, however. It's still there. The other 2 p orbitals are part of the hybridized orbitals, and there are 3 sp2 orbitals. So now, bonding of ethylene. Now, ethylene is a multiple bond. It has a double bond between 2 carbons. There we go. Let's draw one of the carbons. These are sp2. So here is one of my sp2 orbitals here. And here's the other carbon in ethylene. And I'm not going to... Now, you guys have to understand that these 2 orbitals would overlap. These 2 orbitals would be overlapping head to head. I'm not going to show that in my drawing because you're going to see in this drawing fairly rapidly things are going to get pretty messy pretty fast. So I'm going to try to minimize my messiness. But these certainly would be overlapping in reality. Okay, I just draw them apart to make life a little easier for me. You can too if you like. So here's my other sp2 orbital here coming towards us. There's the hydrogen. And here's the other sp2 orbital from the red for the red one going back away from us. 120. This is also 120. Okay, I'm going to get rid of that one though because that's going to be in the way here in a minute. There we go. So there's all my sigma bonds. Sigma, 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 sigma. Now, we know that ethylene has a double bond, so we have to draw the double bond. Now, we've so far seen sigma bonding. Now we're going to see pi bonding. So on each orbital, on each atom, there's going to be an unhybridized p orbital, which I'm going to draw in black on both of them. That will overlap top and bottom. So this is 1/2 of a pi bond up here, and this is the other half of the pi bond down here. Now this is not triple bonding. This is not triple bonding. There's no octet rule violation here. What's happening is that the top lobe of this p orbital, of these p orbitals is overlapping, forming a bond, and so is the bottom lobe. They're both sides are overlapping. Okay, so this overlap here plus this overlap here makes one pi bond. Okay. So the top part is half of it, the bottom part is the other half. And this is what anything that's any period 2 element that's double bonded will look like this. Okay? So if you have a double bond with, I don't know, oxygen to carbon, carbonyl, it's going to look similar to this. If you have a nitrogen to oxygen double bond, similar to this. Okay? sp orbitals. There we go. So now, notice these are sp orbitals. It's one s and one p orbital combined. 2 unhybridized p orbitals remain. And as you can see, they look very similar to sp3 and sp2 orbitals. They're not that different. I mean, sp orbitals will be shorter and squatter and fatter because they have less p character and more s character. But when you're drawing them yourself, they'll look basically the same. And the geometry is the geometry is linear, the molecular geometry. And the bond angle is 180. Let's take a look at a molecule that would have sp hybridization. sp and sp. Okay? sp orbitals are like this. Look just like sp3 and sp2 when you draw them by hand. If you have a computer, you can tell the difference. So there's carbon. And here's my other carbon. Let's make it red. And here we go. Here's one of my sp orbitals. And here's the other one here. There's none. And then notice, a lot of times I leave out the little nubby thing. It's kind of a habit I've gotten into. It's a bad habit. It has to be there, but sometimes it just gets messy. Okay? There we go. And now these are going to overlap. Now I haven't made them overlap for neatness sake, and you're going to see here in a minute things are about to get medieval. So let's draw one of my p orbitals here. There's a p orbital. Here's the other one. And they overlap like this. So far you've seen this before, right? But remember, there's 2 unhybridized p orbitals on this molecule. The other one is at 90 degrees to the blue one, and it's going to look something like this. I know, it's messy. So here we have 1/2 of a pi bond. Here we have the other half of the blue pi bond. And then we have the purple pi bond. There's 1/2 of it, and the other half is back here. I know, it's messy. It's hard to look at. I get it. I'm not Rembrandt. But your book does have nice drawings of these that you can see, and you can kind of get a better feel for it once you look at their much nicer computer-aided drawings. And here's a summary of hybridization and geometry. If you have two hybrid orbitals, you have a linear geometry, and you are 180, and you are sp hybridized. If you have three hybridized orbitals, you are sp2, your bond angle is 120, and you're trigonal. If you're sp3, you have four hybridized orbitals, you're tetrahedral, and your bond angle is 109.5. You will have to be able to identify atoms that are sp2, and sp3 hybridized by looking at them. Generally speaking, but not always, any period 2 atom that has 4 sigma bonds will be sp3. Any period 2 atom that has 3 sigma bonds and 1 pi is sp2. Any period 2 element that has 2 sigma bonds and 2 pi bonds will be sp. Now, in general, that means if you have a triple bond, you're sp. Be careful. For example, CO2. You see here there's a double bond, here there's a double bond. Everyone wants to call that sp2. This is sp. Now what I want you to do is I want you on your own to draw molecular orbitals of this. It's challenging. Also try some easier ones. Maybe try this one. And maybe try this one. Okay? And see if you can draw molecular orbitals for those on your own, and talk to me about it during class time. See if you can do it. This will be part of, this more than likely will be part of your exam, so you're going to want to know it. All right, guys? All right, from there, we'll just leave it right there. We'll come back. We'll talk a little bit about bond rotation. For now, I want to wish you all good luck and good chemistry. We'll see you soon.